Vasavi College, can you hear me? If you can hear me, raise your hand, please. Yes. Thank you very much. Thank you for this joining us in this course, QEEE course, a very different kind of course called solar DC. This is a totally new topic. There is two components, solar and DC. And what I am going to do in the 5 lectures plus 1 tutorial is bring forward this new concept to you. How can you power residential and business sectors using this solar DC? So I am talking about two things, solar and DC. DC power as opposed to AC power. The first question that will come into the mind, and that is a topic of my first lecture, that are we pushing the world backward by talking about DC power? In fact, I am making a very bold statement today. There is a city called Sasaram in Bihar, India. I don't know how many of you have heard of it. It's a very famous city, made famous by a person who got elected about 9 times as MP from this city, Shri Jagjivan Ram. In about next 6 months, this will be probably the first city in the world where every home will have a DC power line. And we at IIT Madras are actually driving this whole thing. What I am making a very, very bold statement after that. In the next few decades, and I cannot give you the timeline, is it going to be 20 years or 30 years or probably sooner? Every home in the world will have a DC power line. And remember that this whole debate about DC and AC took place 100 years back, and the world decided in favor of AC. So what is this crazy thing that we are trying to do in a city of Bihar? And what is this bold projection that by 2035, 2040, maybe by 2045, all homes in the world will have a DC power line? Have we gone crazy? Is this really true? If so, why? Are we pushing the world a century back? What has changed? And why now? Why are we talking about into 2015? If at all any of these things is true, why was it not thought about 15 years back or 10 years back? Before we answer this question, let's just go through this debate. What happened? What we know of in the history, that in 1880s, that is how many years? 135 years or 130 years back, there was a very big battle, and it's called War of Currents. This War of Currents is there now pretty much. You can see this, you can Google War of Currents and you can get that. It was in late 1880s, and this war was taking place between two people. One was a Thomson and Edison, and I think all of you heard of Edison. And the second is Nikola Tesla. Nothing to do with the Tesla that our Prime Minister visited, and yet there is a link, important link. It was embroiled in a battle of war. Now believe it or not, Edison wanted DC power. Tesla felt that DC is the wrong thing to choose. It will be AC power. Now it was not just a war between two people. It was war between two corporations. Edison had this Edison Electric Company, and Tesla was heading another company, Westinghouse. Was it Westinghouse? Westinghouse. That Edison has become General Electric today, and the Westinghouse is what company today? I don't know, doesn't matter. 100 years back this war took place and it went on for several years. In fact, it's a very, very fascinating story. The war was so bad that every day in the media you hear about various wars that takes place and battles that take place nowadays between two political parties or two corporate houses. That's a kind of war that was taking place. And people were using all kind of gimmickry to prove that AC is superior to DC or DC is superior to AC. And technically neither of them were winning. It is at this time that Tesla believed that alternating current is the way to go and will be the future. The decisive edge came when a transformer was produced. Essentially, if you took a DC power, and DC power was done at 110 volts first in the United States, had a small transmission range of 1 kilometer. So if you had a generator, only in 1 kilometer radius, you could actually light up the homes. It was also known that the power doubles, wire cross section will need to be increased by 4 times to keep the loss same, because if power doubles, the current will double, I square will become 4 times, the resistance has to go down by a factor of 4, and therefore wire cross section has to go up by a factor of 4. So you need much thicker wire, and therefore DC looked like this 110 kilovolt DC can only go 1 kilometer or so. What was done with a transformer was something different. With AC voltage, one used transformer and say, I will transmit at a much higher voltage. If you are going to transmit at a much higher voltage, your current will come down. And if your current is going to come down, I square will come down considerably and you can go much longer distances. This was the reason why Westinghouse in the United States took a patent of these transformers which were actually developed. And who developed these transformers? Well, transformer was initially developed by William Stanley, and then this Hungarian group of 3 scientists who really actually perfected the transformer, who produced the transformer. And therefore Westinghouse went and took the patent from these 3 Hungarian companies from Europe and sort of say, we will now take AC line rather than DC line. For the next few years, AC line and DC line coexisted, but the DC line had a problem that you couldn't go more than a kilometer. AC line you could go much longer distances, and in a relatively short time the DC started disappearing. And as DC started disappearing, and this happened long back, AC development started there. All the R&D went on in AC, and therefore AC was very clearly the long distance transmission. So if you are going to transmit something between one city and another city, it is going to be AC. It was also in distribution. So from the substation, if you are going to bring the power to each home, it must be AC. And if it is going to be AC, of course there were transformers in between. And if you are going to, what about at homes and offices? You will put AC line. 110 volt line in the United States, in Europe it became 220, 230, India we adopted 220, 230. All homes and offices started AC line, and that's what we have. What is more important? AC appliances. All kind of AC appliances came in. Lights, AC fans, motors, and motors are really part of this. Fans, refrigerator, air conditioner, mixers, washing machine, everything became AC. The televisions, displays, everything was AC, because AC is all that was available. AC at 50 hertz in Europe and in India, at 60 hertz in the United States, that became the dominant, and everything worked on AC. AC was perfected. In fact, perfection went on to such extent that some 15-20 years back, or probably slightly earlier than that, this what is called miniature circuit breaker was developed, MCB. Today we have MCB. I remember when I was young, there used to be occasionally people used to hear about shocks. Now with the MCB, even if for some reason you touch the 230 volt, MCB will cut off power almost instantaneously and human lives will not be lost. So the MCB actually made home safe. These are all for AC. On the other hand, very little development took place in DC. That battle was finished and no new R&D went on, and AC went on ahead. So if you look today, AC looks far ahead of DC. It is not that there was no debate. There's a very interesting thing that we found at the beginning of 20th century. In Chennai city, in this city where I live, where many of us live, there was a debate going on. How did we get to know about it? In the Madras archives, Tamil Nadu archives, we actually found those papers. So there was a big debate taking place sometime around 1911 or something like that. And there was talk about in India, in Chennai, should we install AC or a DC? The world was veering towards AC. But yet the debate was. And some of the interesting aspects of the debate was, there was a government order objected to conversion of DC to AC on the grounds that calculations showed that AC fan consumed twice as much power as a DC fan. 2 times. This was known in 1911, 1913. This all of us had forgotten. When I studied electrical engineering, nobody told me that. This was known. Why? Because DC somewhere disappeared. There was also talk about, should we government also fear that a mixed system of AC and DC would produce endless trouble and inconvenience to consumers and owners of the building in which electric apparatus was involved. And there was this debate, but for a variety of reasons, because of the way the world was moving, it was AC, AC, AC. And all this talk about, is DC more efficient? Obviously it is not, and somewhere it was buried. No new R&D took place, and therefore over time AC looked far, far ahead. Continued. This happened in 20th century. A totally different incident occurred in the late 20th century. In late 20th century, suddenly something totally different appeared. High voltage direct current, HVDC. HVDC suddenly started being used for electrical transmission when the distances involved are very long, and where otherwise the losses will be very, very high. For example, India was building between Nepal and Delhi a very high voltage link. It was going to do a bulk transmission, large amount of power, and work was done. It's clear that HVDC is far superior to AC. So it is not, even in transmission, it is not really true that AC alone is the way to go. Now this took place in spite of the fact that very little work went on DC. And today, what is the main reason? I think your teachers can actually teach you much better, but all that I can sort of say, the one key reason is that whenever you transmit high voltage, very high voltage, essentially there is something called skin effect. The power gets transmitted on the outside, on the surface of the conductor, and therefore the resistance that they see is much, much larger. That's what happens when you do AC. When you do DC transmission, it actually goes through the complete core, and when it goes through the complete core, the resistance is lower, and therefore suddenly it was very clear that HVDC, at least for long distance, where you care about power losses, it would be a superior technology. And many, many places HVDC started getting used. Similarly for underwater power cables. Underwater power cables are extremely important, for example, to put optical fiber. When you are putting optical fiber between continents, you actually have to feed that with power so that you can put repeaters. And for that, it was very clear that DC or HVDC is superior than AC. It gives you much less losses. It avoids heavy currents to charge discharge. This capacitance created a lot of problem, because capacitance was no longer only in the air now, capacitance was in water, and that created a lot of problem. Now of course, if you are going to do DC and the power that you are utilizing is AC, the power that you are generating that is AC, so you have to do AC to DC conversion. Now AC to DC conversion in around 1900 virtually could not be done. By 1980 you could do that, 1990 you could do that. It was expensive. And even at though it cost more, it was still considered superior because of the other benefits. And therefore, HVDC today has a place, and a very strong place. For example, another thing, if you remember, few years back, the whole of North India grid failed because everything is a single grid. Any great disturbance takes place, the whole of the country can go down. We no longer are using something like this. We have isolated grids. We have one grid, we have second grid and third grid, and they are not connected using AC, they are connected using DC. When you connect them using DC, disturbance in one does not get transmitted to the other. So for unsynchronized grid, it has become very, very important. It improves stability and economy of each grid by allowing exchange of power between two grids without carrying the disturbance from one to the other. And today HVDC does play an important role, and we'll see more and more power transmission. I don't know how many of you have heard that our Prime Minister has kind of proposed that southern part of closer to the equator, there are countries, if you look at the closer to the equator where India is, or many other countries, is African countries, some of the maybe Latin American countries, they are all relatively less well off compared to the countries which are in the northern half, which are in the other upper half. And we all have very heavy sun, most of us. But the problem with the sun is that sun comes around in India, for example, 6:30 AM, goes down at 6 PM. And there also it peaks, and by evening sun is very little. So we cannot get sun power. But do you think about it, that while it is 6 PM at our place, it is 3 PM in Saudi Arabia, and it is 1 PM to Ethiopia. If there is a way by which all of us generated power from the sun, and we connected all the power and transmitted, we can actually get the sun pretty much all the time. And our Prime Minister sort of said, why can't something like this be done? It was somebody proposed it to him, said looks like a good idea. And if you ever do that, it is going to be HVDC. So HVDC has established a place, but this is high voltage DC. Am I talking about this? No, I am not talking about this. There is another thing that took place, less understood. And this is in 80s, late 80s, beginning of 90s, at the time you were born. What happened? Electronics started getting inside the home. Till that time electronics was not there much. It was hardly there. It came in with television, came with all kind of transistor radios, came with wireless phone, mobile phone, tablets, computers. Today you cannot live without electronics. What was the reason why only in late 80s this electronics came in? Before that, when I was a student, for example, if you made a radio, it would take 300 components which will individually transistors, resistors, capacitors, inductors, and we'll solder each one of them. Each of the component was expensive, soldering was a problem. Any component fails, the whole thing will go for a toss. For example, I know I had a small radio when I was a student, and it used to keep on failing, and I had to open it up and figure out where there is a dry solder and try to do something, and sometime it will work. They were expensive. The cost was not going down year after year because there were so many components. Each component costed money. What happened is the integrated circuits came in. What is an integrated circuit? That you actually grow the device on a silicon wafer. You create a mask, put in some chemical, put another mask, put in another chemical, like as if you are doing boutique printing. The cost is in development of the mask, initial design. After that, you can actually stamp out the integrated circuits in tens of thousands or hundreds of thousands with only minor additional costs. What was also very important, that the question started raising, how close can you make the two devices? How small can you make the two devices? How close can you make two lines, two conductor lines? Now it depends on what is the photo resolution. And if you can improve the photo resolution, you can actually make closer and closer. And people started improving that. And improving in such a manner that one Gordon Moore, who's the founder of Intel, kind of sort of say, looks like every 12 to 18 months, we are making our device smaller by 2 times. And every 18 months, therefore the cost will go down by 2 times. Therefore, the power consumption will go down by 2 times, size will go down by 2 times. And he thought that this can go on for next 10 years. And this Moore's law has continued for last 35 years. Every few years you hear we have reached the end, but somehow it continues. And what happens? The cost of electronics keeps on dropping. So if you get a new phone, let's say an Apple kind of phone with all kind of touch phone, it used to cost 50,000 rupees. And now Apple may not come, but somebody else will come, more or less equal kind of phone at 5,000 rupees. From 50 it goes to factor of 10 times. Why? 6 years has gone by, 8 years has gone by, and every 1.5 years it becomes half, every 3 years it becomes 1/4, every 6 years it becomes 1/16, every 12 years it can become 1/1000. And we have been riding on this electronics revolution, and the whole thing is far more reliable because you are not making individual component and soldering them together. Whole thing is made together. Once you make it properly, nothing can happen, nothing moves, there is no moving part, and that made electronics. Electronics got into every aspect of our life, and today we can think of our life without electronics. See, could you have thought of I am giving you a talk from this remotely to so many colleges without electronics? We are using video, we are using camera, we are using this whole displays, everything it is electronics, electronics, electronics. But did we think about it? All electronics is DC. There is no AC electronics. There is nothing called AC electronics. All electronics uses only DC power. What is this? We have been talking about AC power, AC power, AC power is the way to go, and suddenly our life is dominated by DC power. Do we think that we don't use AC power? What do? We use AC power and therefore we use a charger. What is a charger? AC to DC converter. Because our computer uses only DC, our cell phone only uses DC. It is the converters that we started building. We take this AC and convert it to DC. And how much is losses in the converter? I have a HP laptop, very high-end laptop. The converter loss is 35%. I have a Nokia cell phone, a good cell phone. Its converter loses 50% of power. We are losing so much power because these are devices are DC, but our lines are all 230 volt AC. Well, this is the first time DC. So we no longer can say, oh no, it's all AC. There is DC in our lives. Everywhere there is DC. Then came another new thing. In last few years, all the time whenever one talks about light, one talks about LED lighting, LED lighting, LED lighting. Earlier there used to be this tungsten bulb and all those things. Then we came into CFL. Somehow we seem to be starting to forget CFL. And we are coming to LEDs. Why? Simply because LEDs are far more energy efficient. 2.5 times, 3 times more energy efficient than CFL, and probably 10 times more energy efficient than those tungsten bulbs that we used to use 20 years back or 10 years, 15 years back. We still find occasionally some. What is more important is all this lighting which have become LEDs are all DC. All the lighting is DC powered. There is no AC power. One may say, no, but I buy a LED bulb and actually fit it into the same holder where a AC bulb is put. Sure, you can do it. There is a AC to DC converter built in there. The AC to DC converter costs money. There is a loss of at least 15%. Plus, there is also, that's probably the biggest source of failure. Every tube light, LED tube light has a AC to DC converter. If we continue like this, every room will have more AC to DC converter than practically anything. If somebody asks a question, what is the largest number of things, now you can't talk about air particles and all that, in any room, it is a AC to DC converter. Why are those AC to DC converter? But somewhere that Tesla had won the battle and say it should be AC. So our power lines are AC. All our devices are DC. Is Tesla repenting? I don't know. That Tesla is gone. But remember, the new Tesla, the Tesla Motors guy, he clearly recognizes that AC is not the way to go. He started with electric cars. Does it use AC? No. It uses only DC. Everything is DC there. He started using batteries, all DC. He is a champion of DC. I don't know that there is any relationship between that Tesla and this Tesla. Maybe you can find out, but it is moved to DC. Displays. Well, at least CRT displays that we all worked, cathode ray tube. All these were starting with ACs, high power AC. That is all gone. Where do you see CRT tube today? There came plasma display, which was already moving from AC to DC. And then came LCD display. And then came LED display. And today it is LED. Why? Far more energy efficient. No point in wasting power. Nobody will use CRT tube today. Much cheaper also because everybody adopted LED displays. LED display is electronics. What is the source of power? Is it AC or is it DC? It is DC. So displays have become all DC, no longer AC. Lighting has become DC. Electronics has become DC. What is the thing that we are using AC in our homes? Well, fans. Sure, we are using fans. While DC is slowly creeping in, one has to use AC to DC converter, losses, less reliable, poor quality. Converters causes power factor problem. Most of us, you know what a power factor is. We are supposed to have a power factor of 0.99. Most converters, AC to DC converter, do not do it. And if I tell my friends out here that you design one with 0.9 and they say yes, your cost will go up by 10 times. So what they say, oh, let's set 0.85 or 0.9 power factor. What does poor factor, power factor means? They are wasting power. All because we have chosen AC. But bigger things are still to come. In fact, recently there was a report that I was looking at domestic power in India. What is it used for? 72% of power is used for lights and fans. Well, lights are all going to become DC. Fans, I said, well, they will remain at least AC. Well, not really. A ceiling fan is a lifesaver for hot country like ours. Well, you can have air conditioner, but most of us live, most of the country live with ceiling fans. These fans were all designed with hub mounted AC induction motor. And 3 years back, I first time started asking question, how much power do they consume? 72 watts. Then I said, what if I reduce the speed? Well, even at the lowest speed, they are still consuming 60 watts. And that's the time I started to figure out why. And actually we found out that all that you are doing is putting a resistor when you are doing it at speed 1 and burning the power. You are really not saving significant power. You are still using about 60-62 watts of power, lower than 72 watts, but still very, very high. This is what we have lived with. This is what we have brought up with. So it was, well, at least something remains AC. Not really so. We suddenly come with brushless DC motors. First time I heard about brushless DC motor, BLDC motor, about 2.5 years back. I said, what is this brushless DC motor? And then I remembered somewhere in 1970, when I was a student, somebody had mentioned to me a brushless DC motor. And then we had dismissed it. We had not even studied, saying that it's extremely expensive. And here was a colleague of mine who said, let's move towards BLDC motor. So what is this craziness BLDC motor? What has changed? And he was trying to tell me BLDC motor will consume only 30 watts. Remember that 1911 Chennai Madras Archives paper which say half the power it consumes? Well, brushless DC motor is a DC motor, it consumes less than half the power, 30 watts. It's driven by DC. What is more important is that you can reduce the speed of the fan, and when you reduce the speed to the lowest, it consumes only 10 watts, 9 watts, 10 watts. Wow. My first reaction was, yeah, but it will be very expensive. Nobody makes it. And a colleague of mine challenged, saying that yes, maybe, but you should look at it. And I started looking at it. First I started looking at it. What has changed? Why will I look at DC motor today? It was always known. Why will I look at it today rather than earlier? The reason for it is another very, very interesting thing that I learned only about 2.5 years earlier. What's called magic of power electronics integrated circuits. What is this power electronics integrated circuit, and what is this magic of power electronics integrated circuit? Remember that I mentioned that electronics never took off till integrated circuits came. And once the integrated circuits came, it became more reliable, it started becoming less and less expensive, consumed less and less power, world started getting dominated by electronics. I went to our power electronics lab. First everything was big, but then it gave me impression that as if I am walking into electronics lab of 1970. Why? I was a student there in 1970, I had seen some electronics lab. Looked like as if I walked back into them. 40 years later, 45 years later, I walked back into them. Suddenly it kind of struck me, what happened? I actually realized that whole power electronics is discrete. Everything is discrete. You have all these capacitors, transistors, inductors, and power electronics, transistors, and they're all joined, soldered. And again I found that while some student was giving a demo, some solder was loose and he was going and hitting, and then he tried to do some soldering. He said it was dry soldering. I thought this is all, we have gone through this in electronics. I asked, where is the ICs? This is what ICs? We are talking about power electronics. ICs are only for low voltage, low current. As soon as you talk about an ampere, as soon as you talk about 10 volt, integrated circuit disappears. So if I am talking about a magnet, if I am talking about a motor, and that's what power electronics dealt with. Even if I am talking about an actuator, moving something, even the smallest power, you need a power electronics integrated circuit, power electronics circuits, they were all available. There was no power electronics integrated circuit. I asked why. So there is no integrated circuit which can handle high power. It's all low power. In fact, over time, it has become lower and lower and lower power. At least earlier you used to work with 12 volts, then you went to 5 volts, then 3.3 volt, 3.6 volt, then 3.3 volt. Nowadays people work only at 0.9 volt, 1.2 volt or 0.9 volt, and lower current. Power electronics on the other hand is going higher and higher and higher up. Then this revolution started. Sometime at the beginning of the century, the change started. And believe it or not, the change was driven quite significantly by Indian researchers in the United States. In fact, a significant percentage of them were IIT Madras alumni. Just happens to be. Probably you have heard of Jayant Baliga. He was one of the key persons who played a role. Probably you have heard of Krishna Shenoy. There are others who actually started pioneering various devices, IGBT, various kind of MOSFETs, and then integrating them onto a power electronics integrated circuits. And certainly by around 2005, 2006, power electronics integrated circuits started coming in. And in next few years, you started seeing them getting combined with a DSP and combined with memory, and they are all same electronics. And suddenly, however, they were driving high power, high current. This is the revolution of power electronics integrated circuit, which took place 5 to 10 years back. What hhappened as a result? Well, Moore's Moore's law start kicking into power electronics. For example, one of the things that I first learned, that now you can take high current and voltage and switch them very rapidly. For a minute I didn't understand how does it help. And then I kind of sort of said, so suppose I am trying to develop some kind of a transformer. What do? I take a magnetic core, put coil around this, pass a current. That current was at 50 hertz, so it was giving a certain magnetic field. If instead of 50 hertz, suppose I did it at 500 hertz, what will happen to the magnetic field? It will go up by 10 times. Well, this much at least I remembered my electromagnetics. If I do it at 5000 hertz, what will happen? It will go up by 100 times. But I need only so much of magnetics. What I can do? I can reduce the number of turns, the size of the magnetics by 10 times or 100 times. And you could see small magnetics, which I had not even imagined. And I found very, very small magnetics, costing practically negligible value because there are only 4 turns. In fact, somebody was once talking about should it be 3.75 turns or 4 turns. How does it really matter? In our time, this used to be probably 3,750 turns or 4,000 turns. As long as you did somewhere close to 3,750, it was all right. But now you are switching at 5,000 hertz. So 3.5 turns is okay. So 3.5 turns. Whole thing can be made very, very low cost, and this is what the power electronics integrated. Tiny magnetics, able to integrate with the rest of devices, and whole thing became smaller, more reliable, much less expensive, and we suddenly started seeing various things. In fact, the first thing that people got, I mean, most of you are youngsters, you will not know, but your teachers are also there. I see 1 or 2 teachers. If you remember that in 2000, when the mobile phone came in, we used to have these chargers. These chargers used to be huge chargers with large, heavy chargers, because they were used to have a fairly large transformer. Now the chargers are these tiny chargers which you barely hold. But the same transformer has become very tiny transformer, very light. The first place where we started noticing this. But in all other aspect, you are seeing now suddenly brushless DC motor, which was just a matter, something that one could imagine only. We used to have one brushless DC motor that somebody had donated. I think it had costed something like 30-40 lakhs then rupees. And as a demonstration piece, we used to have in IIT Kanpur. Now you can make a small BLDC motor. You can make what is called variable frequency drive. You start with 50 hertz, but don't stay with 50 hertz. You can change the frequency. If you can change the frequency and drive the motor speed can keep on changing, and yet you can get high efficiency. Earlier, only if you run at 50 hertz you could get a good efficiency. Now you can change. I was always wondering this, this air conditioners that work, they turn on and then they turn off. After 10 minutes, they will again turn on. There is only turning on, turning off. Why? Because they are all designed to run at single speed. So they turn on, cool, if they become cool enough, then they just settle down, stop working, till it starts becoming hot, and when it starts becoming hot, you again try to cool. All the time you are trying to do. Same thing happens in the refrigerator. So, I used to ask, why can't you run it at a lower speed? Because they are all fixed frequency drives. Now these variable frequency drives you can use, and you can run it at the speed that you want and still get the efficiency. How much improvement in efficiency? I was shocked that 30% improvement in efficiency. And I was even more shocked when I was told that whether you are talking about BLDC motor or variable frequency motor, they are all DC power driven. DC power driven. BLDC motor can be 40% more efficiency, or even more. And they are all DC powered. You can't use a 50 hertz AC. You take 50 hertz AC, if that's what you do, convert it to DC, another of that converter. Remember that? And now use power electronics circuitry to design the pulses that you want, the shapes that you want, the frequency that you want, and then drive the power electronics integration circuits. So all motors are suddenly becoming, and suddenly I found that therefore a ceiling fan consumes only 30 watts instead of 72 watts. I threw a challenge. How inexpensive can we make it? We started working with companies like Crompton Greaves, with TVS Lucas. Initially it looked very expensive. In less than a year's time, and we are just making 100,000 numbers in a year now, not more. The cost differential for a AC fan is cost is around 1400 rupees, DC fan is 1575 rupees. And I have been told that this 100,000 becomes 1 million or probably 5 million, the cost differential will become zero. And somebody had told me that ultimately your DC motors are going to be, DC fans are going to be cheaper. Finally, when you really get the value. But they are all DC powered. Then one sort of say, well, fan has gone, but what about refrigerator? Well, refrigerator is essentially a motor. Compressor, but compressor's main energy consumption is in motor. There was an AC induction motor that can be replaced by a BLDC motor. I had one of the youngsters actually do that, 30%, 40% power saving. Air conditioners, what do they have? They are essentially motors, again in a compressor. Again you can replace the AC motor by a DC motor. In fact, some of you may have seen Sachin Tendulkar advertises this new air conditioner and say this new air conditioner is far more energy efficient than the old, there's some Korean one he advertises. Actually he calls it, it's inverter based. What is this inverter based? Essentially it's a DC. You take AC and you convert it to DC and then drive. Because people don't understand it today, AC line is all that comes, they call it an inverter based. So brushless DC motor, and brushless DC motor is only the beginning. I'm told that SR motor is going to soon be available, which is even better. And then I don't know, all these power electronics guys are suddenly bubbling with energy. They may come up with yet another motor, which will be even more efficient, lower cost. Suddenly this whole world is changing, is moving towards DC. So drive all DC powered devices of the present and the future. And then nowadays, in all these buildings we put all these sensors. When you put your tap and you put your hand near it, suddenly the water starts flowing. There is no longer faucet. You enter a room, lights come in. They're all sensors. Sensors with sensors that your hands are close to the tap. Sensor with sensors that you are present into that bathroom. All these sensors work on DC. There is no AC. Each one of them you have a AC to DC converter. Remember that AC to DC converter? AC appliances will slowly fade away. And we'll have multiple large number of AC to DC converter unless we change that. But there is more. There is not in fact my first interest in power, and I am really not a power faculty. I am a telecom faculty, communications faculty. I have worked in wireless in local loop. My first interest in all this took place when I was trying to sort of say, why can't I power my office and my home using a solar panel? I actually got one. I got a 125 watt solar panel and we saw the power coming in. By the time the power was coming in, it was less than 100 watt. So first somebody tried to tell me, oh, because sunlight is not a peak sunlight. But then we were sitting in May in Chennai and it was around noon time. Sun cannot be brighter than that. Say, still are you getting 100 watt? And so I said, no, there is a AC to DC converter, DC to AC converter. Solar panel only produces DC. And you are using AC. My fan was AC, my light was AC. I was converting from DC to AC. See, in that 15% minimum loss. Say, can you not reduce it? They said, no. I said, no, I'm sure you can do it. Finally, somebody gave me, see, the cost will be equal to that of the solar panel and maybe we'll reduce it to 12%, 11%. So we're again wasting a huge amount of power. We use solar panel on the rooftop, we convert DC to AC. And then whenever I was using solar and sometimes the solar used to little bit dip because a small cloud came in. And suddenly my lights will start dimming and then they will go off. The point of all, your solar has gone down. So I asked one of my students, why don't you put a battery? So we went and put a battery. And she did all the electronics for that. By the time the power came out and came from the battery, I saw that it was not 15% loss, but almost 60, 50, 65% loss, 60% loss. I said, what happened? Must have done a poor job. I said, no, sir, I did the best. And then we started figuring out there was AC and there was a battery that she was using. Battery was storing only DC power. So she was converting AC power to DC power, obviously. In that there was 15% loss. Then when I needed power, she was taking out DC power and converting DC power back to AC power. There was another 15% loss. 15% loss from solar DC to AC, 15% loss from AC to battery, 15% loss from battery back to AC, 45%. Then I was told about 10 to 12% losses due to battery itself. You are converting into chemical energy. And then 4-5% was left. I knew that much could have been the wiring losses and all that. You are left with 35%. We are putting 125 watt of solar panel. Even in the peak time, we are not getting more than 40 watts. If it is not 12 o'clock, it is 11 o'clock, we are getting only 30 watts. What's the use? And we are paying huge amount of money. And nobody seemed to understand, nobody seems to bother. And that's the time I sort of said, well, there seems to be something wrong. Why do we need so many AC to DC, DC to AC, AC to DC converter? Can't we get rid of them? Say no. And that's the time I sort of say, why can't our power line finally change to DC? So all appliances are AC. Looks like when you are bowled and caught and LBW and stumped all at the same time. No way to go. What do you do? And that's the time we sort of said, well, we will bring in a DC power line to every home. If nobody else builds, we will build all the DC appliances. And our journey begins this, to put a DC power at home. Well, it has been 2 years. We have built many things. We will talk about many of these things. And initially, people used to sort of ask the same thing, are we crazy? Occasionally we still get that. But then we saw everybody slowly starting to think in that direction. It's so obvious, it doesn't take too much. What I've talked about so far in the last 45-50 minutes is no rocket science. After all, we are working with electronics. We seem to forget that that is DC. LED lighting is all DC. Displays are all DC. Fans are becoming DC. Motors are becoming DC. And therefore, all the refrigerators and air conditioners and washing machine and mixers are becoming DC. And sensors are all DC. And everywhere AC to DC converter will be required. Solar panel is DC. In fact, wind power produced is also DC. There is no AC power produced. Battery stores only DC power. Battery gives out only DC power. Where is AC? Just because in 1888 Tesla won, we have to continue to suffer? I said no, we will move and the whole world will move. And we decided to build it, and we decided, and I'll talk more about it, and I'm very certain that it is a 20 years or 30 years. Now there are enough people saying that, enough people are looking at it, they are making standards that it is going to be DC and DC and DC. I think I'll stop here for our first lecture by sort of, maybe to begin with you can have a AC power line and a DC power line in the transition period, because people are still having lots of appliances which are using AC and gradually move towards DC. Well, I'll stop here and throw in a first quiz to all of you. 2 small quizzes. In fact, I just realized that the first question really I've not covered. I'm going to cover it later on. But still it's all right. It's a good question. You can make you think. So the question that we'll ask, suppose I use low voltage. Suppose I use 40 volts. Question is, at such low voltage, what requires protection? Well, which is true? Does AC requires protection? DC requires protection? Well, the next two are just the reverse of it. So if AC requires protection, is A is right, then C is not right. I think my TA who tried to formulate the question could only find two answers. And does AC require protection? Or AC doesn't require protection, or DC doesn't require protection? Now, there is only one class that I can see. Of course, the others can vote. I can see this Venkatesh, which BMS? BMSC. Can you people tell me which is the right answer? Is A the right answer? Raise your hands. Is B the right answer? DC requires protection at low voltage. Is C the right answer? That AC does not require protection. Or D is the right answer, that DC not require protection. I don't see any hands being raised. Raise hand for those who believe A. Wow, AC requires protection. Those who believe B is right, none. Those who believe C is right. Those who believe D is right, DC doesn't require protection. I see some hands. Well, the right answer is neither AC nor DC requires protection. At low voltage of something like 40 volts, it doesn't require protection. So both C and D are right. A and B are not right. I think next question also has been made. I think this, you could find only two answers, and therefore had to do. Most of the electronics are AC powered or DC powered or both or none. Now, this is an easy question. Those of you who believe A is right, raise your hand here also. Please, those who believe A is right. Those who believe B is right. Yeah, at least the most of, and of course C and D cannot be right in that case. All right, that's what it is. So I think I'll stop here. If you have some questions, I can answer some questions. Lakshmi, you have a question. Can you tell me what the question is while she's still trying?
The same college has asked a question through chat.
Okay.
Wouldn't it be expensive to replace AC lines with DC lines?
The question that has asked been, will it be expensive to replace the AC line with DC line? Is that your question? Yes, I think this is a very good question, and in the course of the talk, we will answer this. I think our last lecture will give you some idea of the actual cost. But let me give you a preliminary. First of all, if you replace all the devices in your room, in your home from AC to DC, you don't need to replace any line. You can use the same line. The same copper wire which carries AC can be used for DC. Now if you do split, if you put it in two parts, then of course you need to separate the AC line and DC line. But remember, does light ever go into your town? Have you heard of inverter? Do you use inverter? Have you used inverter? Yes or no, you have to say yes. Yes or no, you have to say yes, inverter. So if you see, inverter is always connected to a separate line. You connect inverter to a limited set of lights and fans and maybe a television or something like that. So you are already having two lines. You can say all the devices which are on the line of inverter can become DC. The remaining can become AC. So you don't need to do a new wiring. Same wiring can be used. In fact, at my home, I have two lines. One is a 5 ampere line, another a 15 ampere line. And they are separate. 5 ampere line and 15 ampere lines are never mixed. So if you replace all the devices on 5 ampere line to DC line, you can use them, and 15 ampere you can use for AC. So there are different ways one can do it, and depends on how much one wants to replace. It is certainly could be a cost and a little bit of hassle, but remember, the amount of savings that you get is so large that in no time you recover that. In fact, the cost of the appliances is something that you have to worry about. If you are going to replace a AC fan with a DC fan, that will be a one-time investment. Even that can be recovered in relatively no time. So yes, but that's an important question. Okay? I think, is there any other question, or otherwise I'll go ahead and not through DC line, wireless transmission of DC. There is already some wireless transmission of power happening, very, very low power, particularly for cell phone charging, but not entirely. In fact, today buses, electric buses are being designed where you don't connect the plug. You actually go over a magnetic charger and it can actually be coupled. So there are some examples of that, but they are all expensive, and I don't see in near future that DC power line in particular, where you want some substantial power like for fan or light. Electronics you may be able to get, because electronics sometimes consume very little power. DC power for appliances, the amount of power, for example, if a mixer consumes 300 watts, I don't see that being easily done through wireless. But then one doesn't know, maybe 10 years, 20 years now, 20 years down the line, one may be surprised. But if you ask me, in next 10 years, unlikely. Final question?
DC battery cost and maintenance cost is more than AC during night hours.
That's not correct at all. DC battery cost is more, battery cost is higher than the grid cost. We'll come to, but I think the question, the DC battery cost is more than the AC battery. There is no AC battery. So more than the AC line, yes. So I'll talk about the cost of the AC grid, I'll talk about the cost of the DC lines, I'll talk about the cost of the solar power, I'll talk about the cost of battery. As we go on, we'll talk about each of them. I'll probably talk about some of these things in 4th or 5th lecture and not now. I'm going to move to start looking at appliances. What has happened to appliances? A very rough picture I've already given you what is happening to appliances. Now in lecture 2, I'm going to specifically look at appliances, DC powering of appliances. Having seen the case for DC power line, let's look at the appliances. Appliances, motors and recent trends. Use of DC power replacing AC power. And efficiencies, availabilities and costs. So I'll talk about that. And if need be, interrupt me out here so that I can ask a question. Television. I don't know how many of you remember this old television. Well, this was a television that we saw in 1990, the first television. And somewhere around 95, 96, 97 we saw that. Around 2000 we started seeing that. Around 2010 it is something like this, 12. What has happened? Sizes have changed, shapes have changed. The latest television, this television is very thin television, goes on the wall, you hardly even recognize. That's a LED, all DC. Electronics and display technology, of course, from CRT, plasma, LCD, we have come to LED. This change has taken place all within last 20 years. Not 20 years, 25 years, not that long. And today it is LED television. We know LED television is far superior in quality, number of pixels that we can get. Costs have very rapidly gone down. And power consumption has gone down. So today, all the older form of television is going away. Even the displays, this thing that you see out here, completely LED LCD. LCD may still exist, but it is LED LCD. Basically, today's LED television, 40% less power consumption, 30% less cost compared to what? Compared to certainly CRT. I don't know that they're really that much less compared to LCD, probably marginally less than LCD. What is the kind of technology? Well, optical LED has essentially cathode, emissive layer, conductive layer, anode and substrate, and essentially completely electronics, all working at a very low voltage, and this is what change has taken place. I'm not going to get into the details of this. This you can, if you want, you can actually go through Wikipedia or any other place where you can see this. Put what is the transparent layer and what is the plastic layer and what is the polyaniline layer. Microwave oven. There used to be a microwave oven till around 65, 70. You could see this microwave oven, heavy power consumption, 3 kilowatts. And sometime around 2000, you started seeing smaller microwave oven, 900 watts. What has changed? That's a question that one will ask. Lighting, again, I've already went through. Incandescent bulb to fluorescent lights to CFL to LED. Look at the number. 60 watts became 32 watts, became 11 watts, and in LED the same thing will not even take 5 watts, it's more like 3 watts. 3 watts. From 60 watts we have gone down to 3 watts. For the same lumens, lumens per watt has gone up like anything. And remember, lumens per watt doesn't give you a very correct picture because LED is a more directed light. When you take a lumens per watt in incandescent bulb, it is on all direction. So that there may be lumens, but they will be spread out. Even for CFL, it is not necessarily in one direction. LED is more directional. So essentially the impact is much more. You can typically say double. So that's what is happening. Lifespan, that's the most interesting thing. Lifespan is much, much longer. We are talking about 36,000 hours, 360 days, 100 hours, means 24. So, well, even this is low. Today's LED bulbs are more like, life is more like 8 or 9 years. Now, if you see, there is electronics and there is this LED. LED has 8, 10, even probably longer. Electronics may fail. Your AC to DC converter may fail. So you have to make sure that that part stays. And this is if it is on all the time. It's not necessarily all the time. What is common to all these? Reduced power consumption. This is one thing that I've been emphasizing. It really saves power. Your power bill can go to half. Just imagine, if you're paying a power bill of 1000 rupees per month, suddenly it can become 500 rupees. Of course, at the same rate. Rate can go up, that's a different issue. But then the 1000 will also go up. Which means in a year's time, you'll save 6000 rupees. Can I replace most of my devices and wiring in 6000 rupees? Probably. Maybe not in 6000, may not be able to do it in all 6000. But maybe in 10, 12,000? Yes. Depends on number of fans. Fans is expensive. Reduce size. Ease of use. Reduce cost. In fact, old ones are not even available today. If you want to try to get these old ones, you can't get. But remember, they're all DC, DC, DC. I think that's another very, very important thing. Everything is DC. What drives this movement from AC, DC common to all appliances? Electronics is the driver. Everywhere it is electronics. And then electronics in laptops, in mobile phones, in computers, speakers, sensors, it is electronics, and everything is DC. So this is what I had mentioned in the last class, and if you really go through, you should try to find out appliances, first appliances in your home which are internally DC powered vis-a-vis AC powered. You will still see many of your appliances will be DC powered because you will have old fans and maybe old lights. But look at what is the saving if you replace that by DC. Just look at it. And what does it really mean? What is the next biggest load? If I go through, stop this, then it comes fans. Fans becomes the next biggest load. All lower middle class homes, it is the fans. You go to upper middle class, maybe fans and air conditioners. Refrigerator is a load, which I didn't mention, but refrigerator is a load. Washing machine can be a load. Water pumps, mixers and grinders. We had a Grundfos managing director, chairman, visiting us about an hour and a half back. And he says, well, all of this is only motor. There is only one thing that I need, is motor. If I can get a better motor, I suddenly can get more efficient. And what is happening to motor? Now, motor is an area which I know very little about. So I studied it in 1973 when I was a student, as an undergraduate student. After that, that time I barely understood it, and I haven't really studied. But yet I'll try to give you some picture. What are the kind of motors that we are talking about? If I look at, there are two kinds, DC motors, AC motors, and these other new motors. These new motors, which we have started seeing in recent years. What is behind this? What was behind DC motor? What was behind AC motor? I've got some understanding. And what I will do is the next 10 minutes, 15 minutes, I'll try to actually convey that to you. What is the basic principle? From what I remember, that if you take two magnetic field, one is a north-south like this, you put another north-south magnetic field. As soon as you put this will move in this direction, this will move in this direction. And there will be a torque. And those right-hand rules, etc. I'm not getting into those details. Let your teachers teach you all this. But we know that if I put one magnetic field north and south, another north-south, it will move in this direction. But that's it. It will move in this direction and stop. So this is not a motor. But suppose it will actually move a little bit more. Suppose at that time, I'm able to change the north and south polarity. If I am able to switch the north and south polarity, then it will rotate further. And if I can again switch the north-south polarity, it will rotate further. So we have the stator, which is always stationary, and rotor. And the whole idea is to create a rotating magnetic field such that it continues. And they are basically two magnets. Of course, any of these magnets can be permanent magnet, or they could be an electromagnet. So essentially, you can have both stator as well as rotor could be permanent magnet or electromagnets. If rotor is electromagnet and if it is fed by DC voltage, the point is, since it's rotating and I need a changing, if it is a permanent, if it is a electromagnetic and it is fed by DC, then I must be able to change direction, and therefore it will need brushes. I'll come to in a minute. It will need brushes. Let me see if I can come to. So it will need brushes. If you see here, I'm not able to show some animation. Unfortunately, it needs brushes. Now, what does these brushes do? That as it rotates, this positive part was feeding this, negative part was feeding this. As it rotates, positive part will start feeding this and negative part will start feeding this. What will happen? The current will reverse. If the current will reverse, suddenly instead of current going like this, current will reverse, the magnetic field will reverse. So I think that is the basic fundamental behind the electromagnet. And if there is fed by DC voltage, you need brushes. Brushes which are touching, but they will change direction. They will be able to change direction. Now those brushes are a problem. In fact, I remember when I was young, I used to live in Calcutta. There the fans were AC. But I used to go to a small village or town in Bihar called Lakhisarai. My grandfather used to live there. And there the fans were DC. And what was happening that I used to spend about 25-30 days, at least one of the fan will stop working. And then a person will come to repair them and he will take the fan out, down. And we are of course too young, but we used to ask what has gone wrong. We were told that brushes have gone wrong. You are replacing the brushes. It was some black color stuff. I remember that. It was a black color. And that used to be replaced and the whole thing used to be put together. Every 6 months or 8 months a fan would require a brush replacement. Brushes also means high losses, because brushes are providing the conduction. It is actually connecting a positive terminal and feed the coil. And since you are making brushes, it is moving on that. essentially there is friction and there is some little gap, there is going to be fairly high losses. So brushes is not good. This was main thing that we talked about, and we are actually told that with AC this will go away. In fact, that was what we were told, and it does to some extent go away. AC at 50 hertz, what happens? It is a 50 hertz. So what does 50 hertz means? That if I am feeding something, it will be positive current will go in one direction. After some time, negative current will go. If positive current is driving something as north pole, the negative current will drive it as the south pole. So I am already getting a switching magnetic field. If I take a stator and I just drive a AC, I am getting a switching magnetic field. That's exactly what those brushes were doing. And maybe I don't need to anymore do a brushes and DC magnetic field. I can put a permanent magnet. And that's exactly the way these things used to work. So start with DC motor. The DC motor, the conventional DC motor, is a motor which have this stator. Could be a permanent magnet, could be electromagnet. And they will have a north-south pole. Electromagnet with DC powered, and they will always have north-south pole. So north-south, the magnetic field will always be in this direction. Will always be in this direction. And then there is loop. It will just not be the loop, it will be loop around a magnetic core material, magnetic core. So it will actually increase the magnetic field. So the current will flow. Now see this current will flow like this for some time, and if once this rotates, the direction will change from these brushes, current will flow in the other direction. So what will happen? You create in such a manner such that initially the north pole is facing the north pole, and immediately there is going to be a swing. Once the swing takes place, now at 90 degrees it could have stopped, because then the torque is for 0. The torque is 0 at 90. The reason it doesn't stop is because there is a momentum. So it will pass through that. Once it passes through that, and as soon as it passes, the current reverses. And suddenly in front of north pole, the other direct thing comes up with another north pole. So it will move and move further. So it will keep on rotating. This is the rotation that takes place. Unfortunately, my animation is not working. The next class probably I will show you. Very nicely it will rotate. And as it rotates, the only problem is as it rotates, the torque will be maximum when the loop is horizontal. It will go to 0 when the loop is vertical, and again maximum when the loop is horizontal. So torque itself will also go through something like this. Torque will go positive, go like this, go like this, like this. Torque will go to, torque is not uniform. That's the only problem. Otherwise this DC motor works perfect. Of course the other problem is brushes. These brushes will wear off and all these things will happen. So then we put this AC motor. Again I can't show you the animation doesn't seem to be working. But AC works at 50 hertz. So this is of course shown as 4 poles, but don't think of as 4 poles. Forget about these 2 poles. Forget about these 2 poles. So assume that these 2 poles are not there. These 2 poles are not there. Assume these 2 are not there. Now what will happen? You think of, assume these 2 are not there, or these 2 are not there. So what will happen? You will get a magnetic field, and you put a permanent magnet. As you put a permanent magnet, and the magnet faces certain pole, it will start rotating. When it rotates, suddenly in the meantime, this will become south, and this will become, right now this is north, this is south, and it will reverse. It will rotate, it will keep on rotating. So that's the first thing that can happen. The other thing that can happen, that you don't even need a permanent magnet out here. In this rotor, you don't even need a permanent magnet. In fact, you can take a magnetic core and with a coil, but a coil which is coil loop kind of shorted to each other. The coil loop is shorted. So what happens when it is moving like this, a current will be produced, and the current will just keep on flowing like this, and it itself will act as a kind of magnet. It's called induced magnet. So you really don't need a magnet. You need an induced magnet is sufficient, and it will rotate. Now, of course, the only problem again is that when it is aligned to the magnet, the torque is maximum, otherwise torque is not very good. And it's because of that the AC motor and the 3-phase AC motor, so this is a single phase AC motor. working principle is the stator winding supplied with AC current to produce changing magnetic field. Rotor is magnetic material with coil loop. Secondary magnetic field induced in the rotor, opposing magnetic field cause rotation, but rotation will not be smooth. Efficiency is therefore not very high, 75% typically. There are all kinds of losses. Core gives you about 25% losses, stator, I square R loss, rotor loss, friction loss, stray loss, so fairly large losses. You also have a very poor power factor. And efficiency decreases on decreasing the load and the RPM. If you change the RPM, decrease the RPM, efficiency decreases like this. And additional energy is consumed in induced magnet. So what is the answer? Well, the answer could be what is called, so the three-phase induction, I'll skip this, three-phase induction motor. So if you take three-phase induction motor, there is a three phases. And now what will happen in the three phase, when the current peaks here, after some 120 degrees the current will peak here, after 120 degrees current peaks here. So inside there is a magnetic field which is rotating, and if you take an induced core with a shorted coil, it will keep on rotating. That's the three-phase AC induction motor. The only problem is they will all rotate at fixed speed. Fixed speed 50 hertz. In fact, the speed can be obtained by motor RPM is 120 F by P. P is the number of poles. So you take 3 poles, so 120 by 3, 120 into frequency by 3. That's the rotation speed. You can't change the speed. If you try to do it at a different speed, you can, your efficiency will go. Most of the thing, power will be lost. So this is our conventional motors that we lived, and that's how your fans was a single phase induction motor, a heavy fan will be 3-phase, a air conditioner will have a 3-phase induction motor, and that's a kind of thing that was used. And then came power electronics. What does power electronics do? We start with AC power, because that's what we have. That's what is available to us from the grid. So we start with AC power. We take this AC power and we convert it into a DC power. We convert it into DC power by just rectifying it. Of course, we lose in the process. Then what we do? We then convert it into whatever pulse we switch. I can create any power waveform as I want. All that I need is ability to switch. And I can make thin pulses if I can switch fast. And today's power electronics integrated circuits enables me to switch that at any speed. And I can create different waveform, one waveform like this, another waveform like this, a second waveform like this, a third waveform like this. And I can have multiple core, one core driven by one waveform, another core driven by another waveform, another core driven by another waveform. And these waveforms have been designed by me. Since they have been designed by me, I can decide when this is north pole, what should be this pole, what should be this one. I can decide, and I can create a rotating magnetic field over which I have much more control. And all that I need is a rotating magnetic field, and that becomes in which a permanent magnet can move, an induced magnet can move, and that's how a new generation motors are made. One of the most common motor is the brushless DC motor, where you generate all these different waveforms. And you can generate them after you convert to DC, you actually switch them, and you switch them using a digital signal processor. You calculate what should be the, when should you switch on, switch off, which of these, maintain the right phase, what magnetic field you want at which point. You just think of magnetic field, a rotating magnetic field that you want. Earlier you had no control. Whatever 50 hertz gave you, you have to accept. Today you have full control. And then you put some kind of a permanent magnet in a BLDC, permanent magnet is put, and the permanent magnet rotates. And rotates very smoothly, no problem, because you have created a magnetic field which varies very smoothly. It rotates at the speed that which you want. You want higher speed, it will rotate at higher speed. You want a slower speed, it will rotate at slower speed, each with full efficiency. because you are controlling the magnetic field. There is no losses. Where are the losses? And therefore, you have a variable speed motor where you have everything controlled. The only problem is magnet. This magnet is neodymium magnet. It requires a permanent magnet. And unfortunately, 87-88% of the neodymium is available only in China. In fact, we have about 6-7%. But there was a treaty signed by our Prime Minister, half of it is given to Japan. So we don't have much. So yes, we can develop this, we will be somewhat dependent on China. Of course, China can increase the price, decrease the price. It had made the price go down to rock bottom. All neodymium mines all over the world closed, and then it increased the price. Then again it has dropped the price. We don't know, we don't have control, and therefore we are dependent. And therefore the next generation motor even becomes even more interesting. It's also a motor which came after power electronics, what's called SR motor. SRM, not SRM, SR motors. SR motor essentially, you can choose the number of magnets that you want, number of poles that you want. You can have 8 pole. In fact, my colleague is designing one with 8 pole. You can have 10 pole. And you can, in each one of them, you put in waveform that you choose. And you, instead of a permanent magnet this time, you are looking at induced magnet. Well, you can create that. You can create windings there also, whatever you want. And then they can rotate. And of course, it's an early stage of SR motor. Initially, it was believed to be very noisy. It was used to be jerky. Now, most of those problems are getting solved. It's a question of, I mean, some of us who have worked in digital signal processing for communication, designing the wave shape that we need and we want. It was initially looked very difficult, and over time, we learned how to do it. With DSP, it was trivial. The power electronics people, to them, DSP is new. So they are starting to do that. They don't know the kind of control that they can have on magnetic field. Of course, your magnetics has to be something that is reliable, same, repeatable, but people are learning very quickly. You can design them. There are tools that are coming, and you can start making motors which are going to be far more efficient and going to work like this. This is what we have. So next generator motor have far higher efficiency, but need DC power to begin with, also called DC powered motors. And for example, if I compare in induction, AC induction motor, speed control is not smooth. BLDC motor provide excellent speed control. Induction motor is considered low cost. BLDC motor, if it is a very small volume, cost will not be small, low. Why? Because electronics is low cost only in volumes. Remember, we are now going to power electronics integrated circuits. ICs cannot be low cost. So if I give my friend here that you buy 100, she comes with a price of $20. I tell her 1,000, she comes with 15. I tell her 100,000 or 10,000, she comes with 12. 100,000, she may be able to come at 7. And I think that's a key trick. So we need volumes. Efficiency is extremely high. And since solar comes on DC, BLDC motor can straight away run on solar DC. And you know, BLDC motor also works as a regenerative brake. So for example, if you are driving a car and you suddenly start braking or slowing down, by slowing down, power can be recovered. It can act as a generator. A motor can act as a generator. And you can, so regenerative power is extremely crucial for auto industry, and these are going to be used in auto industry also. Variable frequency drive, where again you take a AC, you convert first to a variable frequency AC. Variable frequency. Why? Because if you drive an induction motor, it is a frequency, the speed is dependent on the frequency, and if you want a different frequency, you have to change the frequency. If you want different speed, you want to change the frequency and still get the efficiency. And how do you do it? First, you have to convert the AC into DC, and then you convert DC back into the required waveform. Again, power electronics, same thing we have started doing, and we are able to start doing this. Similarly, when motor drive a fan, airflow takes place. Input power is equal to voltage into current. Mechanical power, on the other hand, is torque into RPM. And you can plot both of them, and there is a point at which it crosses. This is the point where it crosses. This is the point where you get the best efficiency, and load curve is tau into R is equal to RPM square, and voltage is proportional to RPM, and torque is proportional to current is proportional to torque. So electric power consumed is proportional to the cube of RPM. So if I drop the revolutions, the speed, motor speed, I can reduce the power consumption like anything. Remember, if I can half the speed, my power consumption goes down by a factor of 8. So when I am running a air conditioner, I was running at one speed and I reduced by a factor of 2, my power consumption goes down by a factor of 8. I think that's a kind of thing that we are talking about. That is the power. These simple things can enable us to get there. Well, advantage of variable frequency drive is it can be retrofitted. It can, you can take even an existing air conditioner and make it run on variable frequency drive and can save on energy. Of course, brushless DC motor has other advantages. Electric vehicles, air conditioning systems runs on motors, etc., etc. Well, pretty much this. At homes and offices, appliances are all moving to DC simply because of efficiencies, not because of AC, DC power and all that. It integrates DC with electronics, becoming smarter and smaller. Question is, how do you want to power them? Do you want to power them using AC and have an AC-DC converter, AC-DC converter, AC-DC converter, AC-DC converter, losses, 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 unreliability, 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 or decide let's move to DC. And I think that's what I am trying to point out, that we can actually strong case for DC microgrid at homes, at offices. Villages can have a DC microgrid, easier to integrate with renewable energy resources, because all renewable energy sources are DC, all storage is DC, and of course appliances are DC. And that's what we want to do. I want to pretty much end here by posing 2 questions, and this time they are right, I hope. Let's take, which of these appliances run on the motor? This is a simple question. I have one of the class, which one? Vasavi, you should be able to answer that. And you people should be able to answer. Air conditioner, fan, TV and inverter. So is 1 and 2 run on motor, air conditioner and fan, or 2 or 3, that is fan and TV runs on a motor, 3 and 4, that is TV and inverter runs on a motor, and 1 and 4 is air conditioner and inverter runs on motor. So which one is right? How many of you believe A is right? A is right? Anusha is saying yes. You know, this television doesn't have a fan to cool it. Okay. How many of you believe answer A is right? Please raise hand. Vasavi? Okay. All right. I think that's the right answer. Which motor has the highest efficiency? Permanent magnet DC motor, single phase induction motor, brushless DC motor, 3-phase induction motor. Which is the highest? Tell me how many of you believe A is right? Permanent magnet DC motor. Anybody from your college also? B is right, single phase induction motor. How many of you believe C is right? Brushless DC motor. There are 1, 2, 3, 4. Most of you are still doubtful. Anusha is still very doubtful. Well, that's right. Well, that's all that I have for today. Next class, we will start looking at the solar panel. And then we'll start looking at batteries. And that's it. After that, we'll be ready to come up with our work on how to build this solar DC system. But questions? I'm here to take questions in the next 10 minutes or so, 10-15 minutes. Yes, please. What is a microgrid? I don't need to go to the slides. I talked about microgrid. Now, you know, there is a national grid. There could be a regional grid. There is a national grid, which is whole of India having one grid. Regional grid, southern region having one grid. There is a distribution grid from substation to your home, to every home. it may have what, 2,000-3,000 homes. And then there is a home grid, you can call it. Home or office, within a building like this, you can have a local grid. As long as you isolate with the other grid, power gets fed from there, but doesn't depend on that. This is a local grid. That a microgrid is essentially a local grid, smaller in size. What is the size? Well, depends. For example, definitely offices can be considered, large office buildings can be considered a microgrid. A village of 10 homes can be considered a microgrid. A village of 100 homes can be considered a microgrid. Depends on what you want to call it. You can even have a single home, once again, you can have even a single home, a microgrid. Particularly a little larger home, your home, you will consider as a microgrid. What about the economics? Well, economics depend on number of other things. How are you feeding? How is the grid designed? So there is no formula. It's a question of the multiple sources of power, If you have multiple feeders of power, then you have to worry about that power can be shared. If there are batteries, power can be shared. At times, you feel that sharing doesn't help. It can even hurt you. So, microgrids, when it comes to, for example, if you have a building, now let me take a very specific question. Take a building, a multi-story building. Suppose it has 12 flats. Should it have a single battery and a microgrid, or should it have 12 homes having 12 batteries? Now let's look at the pros and cons of that. We'll discuss the battery later on, but if you have a single battery, what is the advantage? That anyone can use small, somebody else can use larger, and still you can manage. If you have, every home has a separate battery. If one home wants to use large, suppose every day they use only so much amount, but one wants to use more one day, cannot use it. And it's wasting because somebody is not using it. But what is the disadvantage? Somebody can use more and just drain off the battery. And you want to just do one little light and one little fan and you don't have power. The same thing that when you even design a water tank. Should you have one water tank for the whole building, or should you have 12 water tank for the 12 flats? It's a question of your sharing. When you are sharing, how should you share? What does it mean? Is everyone going to bind themselves by rules, etc.? The problem is a little more complicated. You have 2 or say 12 solar panels. Now if each of them have their own solar panel, if one of them is not using it, others are wanted it but could not use it because you have isolated grids. If you combine them, then if one of them is not using it, other can use it. So certainly sharing helps. It saves resources. It less wasteful. But sharing also without discipline can cause problems. Now the only other answer that I will give, if the sharing becomes over a very large section of people, it can also create instability in certain situations. I think that's another aspect that you have to, technical aspect that you have to look at. Okay, so I think we can discuss this more as you go on. Any questions from anybody? Yeah, please. Yes. They use DC fan. I'm not sure. I don't think they use BLDC. They use brushless DC fan. They used fans with brushes. Now recently they have started using it. They may have started using it. Till 10 years back they were using fans with brushes. DC fan but with brushes. Yeah, because there is no AC grid coming in. They generate power, so they keep it DC. Okay? Alright. Thank you very much. you.